Okay, Zoom folks, is the audio coming through okay? Yep, sounds good. All right, great, glad to hear it. All right, so let's pick up with where we left off last class in thinking about logistic regressions. So logistic regressions, like we said, are those in which your dependent variable is a binary yes or no variable, right? So we talked about things like classifying whether a user is a bot or a human, whether an email is spam or legitimate, or whether or not you are likely or not likely to get sick given some set of predictive variables, right? So in this example, you have some predictors like, do you take a flu shot? Do you take some vitamin C supplements, and how many milligrams? How much sleep do you get every night? And then whether or not you get sick is your dependent variable, right? And the idea behind a logistic regression is you're trying to predict whether or not you get sick, but how likely it is that you'll get sick, right? Because unlike a linear regression, you're not looking for some value. You're looking for the odds that it'll happen. So, like we said, the way to interpret odds or logistic regressions is to look for what we call an odds ratio. And so, an odds ratio is the relative rate at which an outcome happens given the values, right? So, if an odds ratio is less than 1, then the outcome is less likely. If the odds ratio is greater than 1, then the outcome is more likely given whatever your predictors are, right? So and we'll see some examples of this when we get into R, and we'll practice interpreting odds ratios. But the one thing to keep in mind is that the odds ratio is not the default output for logistic regressions in R. That's called log odds. So you need to exponentiate your log odds to get your odds ratio, right? That's the one extra step that you'll have to do. And when we go through this in R, you'll see plenty of examples of it. So in this case, yeah, this is just exponentiate. You get your odds ratio, and then you can interpret it. So if your odds ratio in this case is 1.05, then every time the credit limit is increased by X dollars, then you're 5% more likely to default on the account. So that is odds ratio. And like I said, once we get into R, we'll practice interpreting it. So just like we did with our linear regressions, there are ways to think about model quality, right? Diagnostic tests and things like that. And the thing about model quality with logistic regressions is that we want to correctly classify each observation, right? We saw this image before, right, where we have some observations that are classified as 1, some observations that are classified as 0. And this observation is classified as 0, even though it is actually a 1, right? So this observation is incorrectly classified. And so when we think about model quality, one of the things that we want to think about is what is the misclassification rate, right? What are the number of true positives, false positives, true negatives, and false negatives, essentially, right? And so what we can do is we can kind of plot all of these out in what we call an ROC curve, or a receiver operating characteristic curve. And generally speaking, what we want to do is we want, well, this is sort of the upshot, is that we want an ROC curve to have as much area underneath the curve as possible, right? So the dotted line here at the 45-degree angle, that's kind of a random set of positives, right? And then the greater your the amount of space underneath the curve, that means that there's more true positives relative to the number of false positives. So what you want is as much area underneath the curve as possible. So that's what's going on with your ROC curve.
We
So there
can't
are
see the slide,
what I've said at the bottom
Professor.
here is that there are additional statistical tests that you can use to continue to do diagnostics, etc. But the big one that we're going to do is plotting the ROC curve and then kind of eyeballing it to make sure that there's some space underneath the curve. That's the goal. So let's pop into R and take a look at what this looks like in practice.
Professor Jeffa,
Yes.
we can't see the slides.
Oh, sorry. Thank you for letting me know. Okay. I did not share. Oh, and you guys were chatting, and I couldn't see your chats. All right. Yeah, definitely yelling at me is the way to do it, because when I'm in PowerPoint, I don't see the chats. All right, where's the share screen? All right. So what I did was I went through the slides, which you have. So You can go back through them if you like, but I'm not going to go back through them. What I'll do is I'll talk through those ideas while we're in R. And then if there are questions, then we'll go back through the slides. Does that sound okay? I hope so. All right. So I updated a new script for logistic regressions on ELC. So this is what, the 11.4 script. One thing that I noticed is that I did put some exercises on the script. And unfortunately, in the version that I uploaded to you all, I put the answers in for the exercises. So, you have those there, which, it's not the worst thing in the world. But I didn't remove them from you on this new version. I said, if you already downloaded the script, then, I'm not going to take the exercises away. But anyways, so we're going to start with this data set, CC data, right? And CC data has a bunch of information about loans. And specifically, it has some information about whether or not the loan gets repaid or not, right? So we have a bunch of information about the borrower. Does the borrower own a telephone? How many dependents do they have? What's the kind of class of job that they have? Do they own or rent a house, etc. Right? What's their the credit amount, the employment status, credit history, all of these kinds of duration of the loan, etc. Right? All of these kind of pieces of information. But the thing about this data set that makes it useful is because the dependent variable, the thing that we would want to predict, is whether or not the loan gets repaid. Right? So that is our dependent variable in CC data. So what we're going to do to start is we're going to take a class, which is which we know will be our dependent variable, whether or not the loan gets repaid or not. And we're going to turn it into ones and zeros, right? So just like we did as factor with our months, we're going to turn class into as numeric, right? So as numeric basically takes those ones and takes the goods and whatnot and turns them into ones and zeros, which allows us to run our logistic regressions on them. So that's the first step, right? And then the second step is to actually run the logistic regression. And so this is going to be a simple logistic regression, meaning there's only going to be one predictor variable. And so we're calling it model 0 log. So just like with your linear regressions, you can call your model whatever you want. It'll create an object. The object will live in your environment, and then you can do things with the object as you kind of work with it. So then a couple of things that are different, right? Instead of LM, we're using GLM for general linear model. And then we have to specify the family, and we're saying family equals binomial. But other than that, everything else is the same, right? We have our dependent variable, which is class, and then our independent variable. And then if we had additional independent variables, we would just put a plus and then the continuation of independent variables. And then our data is going to equal CC data, right? Which is the name of our data set. So in this case, we run that line. We have model 0 log. If we look at the summary, we see that there's some things that we recognize, right? So we see, okay, duration is what we were looking for, right? The duration of the loan, does that help us predict whether or not the loan gets repaid or not? So the coefficient is negative, right? What does that mean? It's negative and significant. So significant is the first thing to really look for. Significant means there is a relationship, right, between your predictor and your outcome variable. So how do we tell that it's significant? We see these 3 stars. That's great. The other thing that we do, the more technical thing, is to look at this right here, your p-value, and that is 4.63 times 10 to the negative 11th, which is less than 0.05, right? Which means that we have a significant relationship. So then the next thing you might look at is what is the direction of the relationship, and that is a negative relationship, right? You've got a negative in front of your coefficient estimate, which means that you have a significant negative relationship. So the longer the duration of the loan, the less likely it is to be paid back in our data set, right? Now the question is, what's the effect size here? Like how much, how strong is this relationship actually going to be? And what we said is that what we have right now are log odds, right? What we want to do is convert to odds ratio because log odds are difficult to interpret, like we said. So for every 1 unit increase in duration, the log odds of a good outcome decrease by 0.376. But log odds is not easy to interpret. So what are we going to do? We're going to exponentiate the coefficients and express them as odds ratios. So that's what exp means, of the coefficients of model 0 log. So we run this line, and then it tells us, okay, now we have our exponentiated coefficients. And so now our exponentiated coefficient for duration is 0.96. So what this means now is we can interpret it, right? We have an odds ratio. So for every 1 unit increase in duration, the odds of a good outcome increase by a factor of 0.9631. And the note here is that this is technically a decrease since the factor is less than 1, right? So for every 1 month increased duration on the loan, you take the odds of successful repayment and you multiply it by 0.96315, right? What does that do? That chips away a little bit at that number, right? So the odds go down and down and down just a little bit for every additional kind of period that the loan is being repaid in, right? And we can tell from CC data, this isn't explicit in the data, but we can infer that, by the numbers that we're talking about months here, right? So 6 months, 48 months, 12 months, etc. So for every additional month in duration, the odds of a good outcome increase by a factor of 0.9631, which is a decrease. So are there any questions there about setting up your logistic regression and interpreting it? All right. So one of the things that we can do then is add our predictions to our data set, right? Because what we did was we essentially did this, right? We made some predictions and we classified them as being good or bad, right? So let's take a look at what that looks like in practice. So we'll run dplyr, and then we'll create a column here called probabilities, and we'll use predict on our model to predict those probabilities, right? And then so we'll say, okay, are those, well, we'll take a look at what we just did, right? So we have probabilities right here, and we can see what those probabilities are, right? And the way that these probabilities work is that if the probability is greater than half, then it rounds up to 1. And if the probability is less than half, then it rounds down to 0, right? That's essentially what we've done by creating those probabilities in the process, right? Which is essentially the same thing that this kind of visually represents, right? So what we can do is say, okay, we can create a column called predicted classes, and this is just a simple, if else, where we say, okay, if the probabilities is greater than 0.05, then that's, we predicted it to be good loan. If it's less than 0.05 or 0.5 rather, then you predicted it to be a bad loan, right? So then you run that, you look at CC data, and so let's see what happened here, right? So for this first observation, the class is 1, which means that the loan was paid back, and the model predicted, 0.80 that it would be paid back. So the prediction was that it was a good loan, right? For the second one, what actually happened? The loan was not paid back. What was the prediction? 0.466. That's less than half, right? Which means that we predicted that it was a bad loan. The third one, it was paid back. 0.77, paid back, good prediction, right? So we go down and we can see that, in general, our model is pretty good. But let's look at this one, for example. In this observation, the loan was not paid back, but our model predicted that it would be paid back, right? We got a predicted good, even though it was not, right? What does that mean? That means that we got, in this case, a false positive, right? Which is our sort of measure of quality of this model, right? So what do we need to do? Or what are we going to do to kind of assess whether or not our model is overall good or bad? We're going to assess the number of false positives, relative to the number of accurate predictions. And the way that we do that is by using an ROC curve, right? So the way that the code works for the ROC curve is that you require a function and then you require some plots for the ROC curve. So if you run these 3 lines, you're not going to get anything yet, right? Unless you have this function in your environment. And the function, I believe, is it lives on line 82 in this version of the script, right? The function goes from 82 to 105. And I put it lower just so that it was kind of out of the way in the moment. But what you need to do is put your cursor on line 82 and then run that line, right? Run lines 82 to 105. And what this essentially does is it creates a function that, again, lives in your environment. It's, this right here. And so you're creating a function that measures your true positives, false positives, true negatives, and false negatives, so that you can then plot them, right? So what I'm not going to ask you to ever create a function in R or even manipulate the function in R. You just need to copy and paste it. But we use the function to create our ROC curve, right? So that's what we're doing here. So if we scroll back up to where we were, line 45, right? We're going to use kind of the base R plotting package. So we're not using ggplot for this. But if we run these 3 lines, right, then we plot our ROC curve. So we've got our true positive rate, our false positive rate, our kind of line of sort of random true false positives, and then we've got in red our ROC curve, and it looks okay, right? Is it great? No, it's not great, but it's fine. And so as we see more and more of these, you'll sort of get a sense of how to interpret this. But for the purposes of our ROC curves, for the purposes of sort of our assessment of our logistic regression models in this class, this is kind of all that I'm going to ask you to do. So are there any questions on this ROC curve generation? Were you all able to get it to run? Anybody have any trouble?
Can you explain the how you want lots of area below the curve?
Yeah, so this red line is what we're talking about, or the red kind of curve is what we're talking about when we're talking about the curve itself. And so what we want to see is area underneath that red line. And what does that mean? That means that our true positives are like where we have more true positives relative to false positives, right? Ideally, we would never have more false positives than true positives. So you'd never see the curve underneath the randomness line, but it might be very low onto it. And I believe that we might see an example of that in the next example, or maybe in one of the examples that we will do that was a practice assignment that I gave you the answer to. So let's see if I can just pull that up. Do I have Superstore here? Yeah, Model 3 log. I've got it. So let's here's another example of one. Oh, nope. This one has even more area under the curve. So I guess you can see some examples of them. There was one, I believe, that was not great. So here's one where you can see that we do run into some problems between the sort of true positive and false positive rate. So here's kind of an illustration of where things might, kind of be a little bit, there's not enough area underneath the curve. So that one that I just ran was on lines 135 through 137. And that model was the model with credit amount, right? So it was, I guess, the first practice problem, simple linear, simple logistic regression. And the model was, does credit amount predict loan default?
Okay, thank you.
Yep, and the script file is on ELC. The 1141 is the one that you want to be using. And I don't think that there are any differences between what I have on my script and yours. I think I saved it and then uploaded it, so there shouldn't be any changes. But if you downloaded the old linear regression script, then there were some updates that I made. So please do use the 1141 just to make sure that you're on the same one that I have here. Okay, so we can do multiple logistic regressions in the same way that we could do simple ones, right? So the example that we had of illness, right? We have multiple predictor variables, right? Flu shot, vitamin C intake, sleep, etc. In this case, this one is a categorical one, right? Yes or no. You get a flu shot, and then how much vitamin C do you take, and then how much sleep do you get? So in this case, there's 3 predictor variables and then a dependent variable. So We can do the same thing with hours, right? So in this case, we will do we'll create a model. In this case, it's called model 1log, and we'll create it with age and duration as our predictors, right? So we look at duration. That was the one that we just looked at in months, 48, 12, etc. And then age, I believe, is age of the borrower, right? So you've got some young folks, some older folks, some middle-aged folks, all borrowing for whatever they wanted to buy, right? So we can create that model exactly the same as before. The only thing that we're adding is age plus, or if we had duration plus, it would be duration plus age, right? That specifies our additional predictor variable. So we run that, summary of model 1log. And what do we have now? We have coefficient estimates for each of our predictors. In this case, we do see stars for both of them. Our p-values are less than 0.05. That means that there is a relationship between both age and duration and our dependent variable of success of paying back the loan, which is great. Now the problem is that we can't interpret our log odds, so we're going to exponentiate, right? So what do? Exponentiate of the coefficients of model 1log, and now we have age and duration. Duration, like we know, right? For every month increase in the term of the loan, the odds of successful payback increase by 0.96, but every year increase in the age of the borrower increases the probability of payback by 1.01, right? So if you go from 25 to 35, that's an additional 10 years, right? So you multiply 1.01 10 times. And so your odds of successful repayment go up, a decent amount. A relatively low amount, I guess we could say, right? So that is how to interpret what we just did there. So the main thing to remember, right? The actual code to run the model is very similar to the standard logistic regression. But the thing to remember is that in order to interpret, we need to do the exponentiate, and then we can interpret the odds ratios. So then if we plot the ROC curve, in this case, here's where I put the code for the formula itself. And once you do that, the function lives in the environment, so you don't need to run it multiple times. Now, if you are knitting the document, right, you need to put the function before you use it for the first time. In this case, I put it lower just to sort of clean up the what things looked like up at the top of the script, which may or may not have been the right move at the time, but it's what I did. But if you're doing this in homework, for example, and I think the homework that I ask for is very simple. I only ask for one thing, so it shouldn't be a case where you might want to put it at the bottom of the script or something like that. But it's got to be before you actually use the function itself, right? And then you run the lines to create the actual ROC curve, and then you have it, right? And you can see, okay, based on this model, how many true positives versus false positives do you get? And as a result, how do we evaluate the success of the model? Okay, so this first practice that I asked you to do, which I gave you the answers to, so it's, but fairly simple. So we'll go over it, right? I said, okay, predict the odds of a successful repayment from the amount of debt borrowed, credit amount. So what did we do? We said, okay, credit amount is going to be our predictor. Class is going to be our dependent variable. So it's the same general format, summary of model 2log. And then we need to exponentiate to interpret the results. We can see that we have 0.9998881, right? And so what does that mean? That means that for every one increased dollar, right, the odds of successful repayment go up by 0.9998881, right? Or they drop just by a very little amount. So your first instinct might be to say the effect size is very small, but the thing to note is that a $1 increment is also a small increment, right? So typically, you might borrow, $500 or $1,000 for, I don't know, some small consumer purchase, right? Consumer debt. Or you might borrow like $10,000, $15,000, $20,000 for a car, or like $300,000 for a house, right? So the sort of scale at which that dollar amount goes up goes up quite drastically, right? So your 0.9998881, it gives you a lot of room to kind of adjust for the scale of the amount of money that you're borrowing. So the next practice that I did here was with Superstore, where we said, okay, we can look through Superstore. And the way that I did it, and I think that I ask you to do something similar on your homeworks, is where I say, okay, this data set is not kind of custom built for a logistic regression. So we're going to do sort of like what we did with categorical variables in linear regressions, right? We're going to have to find some cutoff and create a categorical or a binary dependent variable that seems right? So the first thing that I say, and this is kind of a throwback, is plot a histogram of Superstore sales, right? And in this case, I think I ask you to change the bin width just to see which is better. And the idea here was that you would, have to go back through your memory, maybe go back through the help of ggplot and practice plotting sales so that you can get a, just refresh your memory on these things. And then the idea here is to say, okay, we want to predict whether or not there's going to be sort of a low or a high sale. And that's our dependent variable, right? So the idea is that you use the cutoff that you got from your histogram to pick whether what that number might be. So in this case, we picked $500. And so we case when, right? So just like we did with our categorical variable. So now our Superstore data set has sales category, right? And this is going to be our dependent variable, right? Where if it's a high sale, it's a 1, and if it's a low sale, it's a 0. And high and low is sort of based on this $500 amount. So that's what we're going to predict, right? Was it a high sale or was it a low sale? So we basically, just like we did with our categorical variable, we took a continuous variable, right? The amount of dollars that a sale was, and we sort of abstracted it out. We removed a bunch of information, and we made it a binary dependent variable. Is it a high or a low sales amount, right? In practice, is this good? Is this a good practice? No, it's not, because what we're doing is we're removing information from a model, and in general, that's not something that we want to do, right? But because we're working with Superstore, we're working with Coffee Chain, and we don't want to add complexity to the homework assignments or the examples beyond the data sets that y'all are familiar with. This is the way that I chose to do it. So then we can take our Superstore data set with our sales category dependent variable and say, okay, can we predict whether or not a sale is going to be high or low from the quantity ordered? And so here what we're doing is we're saying, okay, the setup is the same. We're using GLM rather than LM. Our dependent variable is the sales category column. And then quantity is going to be our independent variable. It's a simple logistic regression. Data comes from Superstore, and then family equals binomial, right? So we run that, look at the summary, exponentiate, and then we can see that, yes, for every 1 unit increase in the quantity, the odds of a high sale increase by a factor of 1.29. So if you look on ELC, you'll see that there's another optional video where I go through this example and one other example in a little bit more detail. What I think it's the video that I tag as similar to homework assignment 8 or something like that, because what I ask you to do for your homework, and this is probably the shortest homework assignment that I ask you to do, is do something very similar to this in Coffee Chain. Just one time, just to show me that you can do it, you can interpret it, and that you understand what's going on. So it should be very, very simple to do. If you think that this lecture has already been going on too long on logistic regressions, you could probably knock out that assignment within 5 or 10 minutes at the most. It's essentially this. But if you're still kind of struggling, you want to see more examples, check out that optional video, and I'll go through some examples like this. And it should help you pretty explicitly finish the homework assignment using Coffee Chain. Are there any questions on logistic regressions? All right, let's do a 1 through 5 in chat. Where I want 2 numbers. I want like a 1 and then a dash and then another 1, right? where the first number is where you started before we got into this class with your sort of understanding of logistic regressions. So like if you were already an expert in logistic regressions, give me a 5. If you were not an expert in logistic regressions at all before this class started, give me a 1, and then dash, and then whatever you feel like you are now, like whether you understand it, you understand how to do it, etc. So like a 1 through 5 dash 1 through 5 to see, where you were and where you are. All right. Okay, so the sense that I'm getting is that a lot of you were not, exposed to these ideas before. Some of you were, and hopefully we picked up some new things. So that's good. Because I was curious also, whether or not I think the other class, the MSBA students, they've all kind of had experience with this, but my sense was that it was not covered in MBA Intro to Stats. I don't believe, right? So. Was it? Did you guys for MBA Intro to Stats? So that's with Paul Holmes, right? Did you guys cover logistic regressions?
I don't think we did. If we did, it was very short.
Okay, and it's also possible that y'all are in that class right now, right?
No, we took it our first semester.
Took it first semester. Okay, so yeah, I guess if you did, it was very short. You don't have much recall about it, but hopefully now you see some illustrations of when you would actually use this, right? Like we said, it's a classification issue. So was the email spam or not spam? Was the user a bot or not a bot, right? And if you have a data set that you can help build a model from, then you can start to predict these things whether or not they are true or not. All right. Oh, and so the other thing that I have down here, which we didn't go over, is using ggplot, how you might make a plot of the observations, and use geom_smooth to see what the model actually looks like, right? Sort of like the example in the slides that looks like this. So this was just sort of an illustration of that happening, and you can sort of see what the model looks like. And did we do the ROC curve for it? I don't think we did, but same thing. The one thing that you would do is you would change, these two, the things that you're using ROC on, right? So ROC is that function, right? And so what are you using ROC on? Sales category, and then model 3 logs values. And so here you can see that there's a good amount of area underneath the curve, which means that the model quality is fairly high. All right. So the next thing that I wanted to cover is another way to think about classifications, and that is with decision trees. And so decision trees are sort of in this sort of abstract conceptual way to think about them. The ways to think about information in a hierarchical sense, right? So they are designed to, where the top is the root node, which means that the tree itself is upside down. And then you have leaf nodes on the bottom that have kind of the likelihood of something in sort of the very bottom cases of the thing, right? So in this case, you have whether the person is employed, what the balance is, what their age is, and then whether or not you're going to write off the loan, right? So there's some indicator. And so a decision tree, each node represents a certain test, right? So in this case, your nodes are, okay, are they employed? Yes or no? And then if yes, then something. If no, then something else, right? And the leaves represent classifications. So it's like, yes, that is the class, or no, that is not the class. And that is the structure of a decision tree. So we'll look at what this looks like in concrete detail in a second, where this kind of nodes and leaves thing will start to make a little bit more sense. But what is the actual classification process? We use something called information gain, or Gini impurity. And what does that measure? That measures the level of disorder in each set, right? So what are you looking for? You're looking for as little sort of chaos within each set as possible. And so if you sort of divide the outcomes by age, yes or no, then this model, this Gini impurity model, will look at all the information and we'll say, okay, these observations go here, these observations go here, relative to how different they are from each other, right? Loosely speaking. If you want to get into the sort of technical mathematical information, there's a link in the slide notes, I believe. Yep, it's there. You can get into the math, right? But let's look at what this looks like in R. So here's our root node, and this is using our credit card data set again. And then we have some internal nodes and some leaves at the bottom. And so the way that I have this set up, I think I have this as a okay, so I have it. Well, I thought I had it with animations. I don't. So your root node. The root node contains 100% of the values, right? So that's that 100% that you can see inside of that node, right? And within the root node, 70% of the values are good and 30% of the values are bad, right? So that's what's happening inside of that node. And then you have two different paths, right? The next thing is, what about the duration of this loan, right? Is the duration of the loan less than 35 months, right? So 36 months, I guess, is 3 years. Is it 3 years or longer or not, right? So if the duration is greater than or equal to 35 months, then you have this is where you land, right? If not, then this is where you land. And so what happens here? Well, the right-hand path is where the duration of the loan is less than 35 months, and that contains 83% of the total values, right? So the majority of the values are going down the left path where the duration is greater than or equal to 35 months, right? So that's that 8317. You can see that it adds up to 100. And there you can see that 74% of the observations within that decision tree are considered good, right? They get paid back, right? Then within the left-hand path, that's the duration of loan that is greater than or equal to 35 months, and that contains 17% of the total values. And of those, 52% are good and 48% are bad, right? So we haven't gotten into this age situation yet. But basically, if we kind of draw a line like that, we've analyzed the root node, we've analyzed the duration yes or no nodes, right? That's where we've thought about. So the top node contains 100% of the values, right? 70% good, 30% bad. And then we go down this duration question. If the duration is greater than or equal to 35, then we have 17% of the values there, and 52% of them are good. If not, then we have 83% of the values and 74% of them are good, right? So then we have the far left-hand path, which is the leaf node, right? It's the bottom level node. Here what you have is the duration of the loan is greater than or equal to 35 months. So it's going down this way. And also the age of the borrower is less than 30 years, right? So what happens here? That contains 6% of the total values, and of those, 33% of them are good, and 66% of them are bad. And so because the node contains mostly bad observations, it goes into blue, right? So if you see a 0.5 or higher, it's going to be a greenish node, and if you see a less than 0.5, it's going to be a bluish node. So this bottom left, the very bottom left node, it contains 6% of the total values. And of those 6%, only a third of them are good and 2/3 of them are bad, right? So we've created a category where it's a long-term loan with a young borrower, and that's pretty bad, right? The other kind of alternative here is that we have a long-term loan with an older borrower, right? So in this case, age is greater than or equal to 57. And so you don't see the yes, no, but we know that yes is on the left, no is on the right, just based on this yes, no. So we have duration greater than 35 months, and then age is greater than or equal to 57 years old, right? And this is 1% of total observations. So there's not a lot of 57 plus people getting loans that have 3-year terms. But of those that do, 1/5 of them pay them back and 4/5 of them do not, right? So that's how we interpret what's going on in this tree. So what are we doing here? This is an unsupervised task, right? We don't know these outcome categories before we start the process. We just let this Gini impurity model figure them out for us, right? And so what are we doing? We're creating customer segments. That's what these kind of these things on the bottom are. So we have a customer segment for people that have a short-term loan, less than 36 months. We have a customer segment for greater than 36 months and age less than 30, customer segment for greater than 36 months and age greater than 57, and then greater than 36 months of loan term, and then sort of medium term age, right? And so what does this tell us? This tells us that the high risk borrowers are either those that have long loans and are very young, or long loans and are very old. But if you have a long loan and you're sort of middle age, or if you have a long loan, or if you have a short loan, right, then you are sort of a fine customer, which is a fairly useful thing to find out, right? Because we found out where the sort of risk targets are in our model. So how do these discussion trees get built? You could create them by hand, right? I think that some professors might ask you to think about a decision tree by hand, just to sort of force you to conceptually think about all the different options, right? But I won't ask you to do that. Instead, I'll sort of illustrate using R how decision trees are learned, right? You put in a bunch of different observations, you let the Gini impurity model work, and then it will come up with a model that will help you decide what customer segments are there, right? Using that model. So how does this work? Like we sort of talked about, it is done in top-down fashion, right? So that means that a partition that's performed earlier in the tree doesn't change based on later partitions. So it's done top-down. So you start with the root, I guess, of the tree, and then you go down one layer. And in many of these decision trees that we do in R, the default is for two levels per level down each line, right? Why is that? That's because of computational complexity. So you can add more levels if you like, but if you have a large data set, then this takes a long time to compute. So for computational simplicity, we do two kind of paths per level. So some advantages: these are inexpensive and easy to construct. You don't have a ton of control, but you can still do some unsupervised learning about your data, right? So if you set up a decision tree and you look at your output, then you've come up with a model that explains some set of potential outcomes in an unsupervised way, right? You don't know what those customer segments are going to be. You have to look at them and then decide how useful they are or are not after the fact, right? Now, kind of the problem is that it's easy to overfit your tree to the data, right? So the thing about it is that if you have the bottom level of a tree that is very, very kind of granular, then you might need to what they call prune it back and go up 1 or 2 layers, right? Because what you've done by going down, maybe from this example tree, right? You add 1 or 2 more layers of this, and you've really started to overfit the data. But you kind of prune it back, and then you're saying, okay, this layer that we have here, it makes sense, right? It's generalizable. We can say, okay, we understand why, short-term loans and long-term loans with, older or younger lenders might have different types of success rates, right? There's a theory that we can come up with that makes sense. But if we were to let that keep going, right, which we could do, then we might start to see things that we can't actually explain. And the problem there is overfit, right? So you've constructed a model that relates so closely to your individual data set that it can't be generalized to other data sets. But in this case, it's not. It's something that we can kind of come up with a theory for, which relates back to the underlying idea, right, of an unsupervised model. It's a data-first model or a data-first approach. And then what happens when you start with the data? The idea is that your conclusion is a theory that you can then test, et cetera, right? So There are ROC curves that you can build using decision trees, but we're not going to get that deep into them in this class. So how do we actually do this? We'll use the packages rpart and rpart.plot. And so we'll use CC data. And I'm going to re-import it because we want to clear out any previous alterations to the data set. So we'll just use class good or bad, right? Because that's more descriptive than ones and zeros when we actually build our model. And then just like any other model that we've done with our linear or logistic regressions, we're going to call those by some object. And then in this case, I'm using an equals sign, but we can assign them using rpart as the function. And then class is our dependent variable. Age and duration is what we're looking for. And so if we run that, right, then we've created that model, right, tree model 1. So we can look at summary tree model 1, and that gives us kind of a summary level of statistics. But this isn't, very easy to interpret because it's giving us a bunch of information about each node. But these models are useful because they're very visual, right? So instead, what we can do is do rpart.plot of our tree model. And once we do that, then we've plotted the model, and this is the model that we used as our example, right? And that is our plot. So what happens if we maybe remove duration, right? So we make this even simpler. Then we plot this, and so it's given us something else, right? So it said, okay, we've got duration greater than or equal to 35 months. Again, so these very short-term loans, that's, those are still generally good. But then of those, right, of the ones that are longer term, if it's greater than or equal to 44 months, then then there's another sort of set of decision points where you might look to see whether or not things are good or bad, right? And so you can add as much complexity as you sort of desire here. So what did we have before? We had age and duration. And let's maybe try adding something. Let's see what we have: age, duration, residence since. So how long they've been at their location. We'll try that. Plus residence since. And we plot it, and let's zoom in a little bit and see what R gave us, right? So the first thing that we have is the duration of the loan. Again, it said that that's the most important thing, right? We can sort of infer by the fact that duration keeps being at the top of our list, right? And then we have age, a couple of age indicators, and then we have how long have they been at their residence, and then of those that have been at their residence for looks like a shorter amount of time, then you look back at age, and then you can create more customer segments, right? So now we've added more customer segments. Now we have 6 different segments when we add that other thing to the model. So this is an inductive approach. It's unsupervised. It starts with the data, but it could be useful, right? Because if we think about things that we independent variables or predictors that we expect might help us predict something, then it gives us some structure to think about those issues, right? It helps us build a theory around them. So that is what a decision tree is used for, and how you might use it in R. Are there any questions about this? All right, no questions about decision trees. So homework 8, you have it available to you. You should be able to knock it out pretty quickly. If you have any trouble, there's that YouTube video that you can watch. Also email me if there's any questions, and I will see you on Monday.
Professor, I want to verify next Tuesday is when the homework's due. Homework 8.
I think Monday. Is it due Tuesday on ELC?
Yeah.
Okay, well, keep it on Tuesday. That must have been a mistake by me, but if that's what it is, then that's what we'll keep it at.
Let me make sure. I might have tripping hell. It's 9th. Oh, that is a Monday.
That is Monday night? Okay.
Yeah, sir.
Yep, that was that's kind of in line with what we've been doing, I think, right?
Yeah, of course. Okay, thanks.